Let's see. Okay, so I think we're live right now because we got this, we got this little button on the top. I think we can wait a few minutes just to wait for people to come from the previous events, and before I can introduce you and we can start the talk.
Sounds great. Do you want me to start sharing the presentation right now?
Yeah, we can start with that. So let's see. Let's see. Everyone. Yeah, and so for the people that are just coming in, if you have any questions, like if you're listening to Carolina and you're like, oh, I got a great question, we're going to do the questions at the end, but you can write them right now in the Q&A, and you can upvote them, and we're going to be able to address some of these questions at the end. So yeah, if you have any questions, just type them in the chat.
Let me know when you want me to start, Benjamin.
Yeah, let's start at 12:05. So just to start, since we're getting close to 12:05, I want to introduce our keynote speaker, Carolina Parada. We're really happy to have Carolina Parada. She's like a really accomplished person, and I'm just going to give you a little bio, but I think Carolina is also going to tell you, a little bit about her during the presentation. And so she's going to give the talk, The State of Robotics at Google. And Carolina Parada is a senior engineer manager at Google Robotics. She leads the Robot Mobility Group and Robot Vision Group. And these groups focus on improving robot motion planning, navigation, locomotion, and also they use reinforcement learning, imitation learning, and many other techniques. Before that, she led the camera perception team for self-driving cars at Nvidia for 2 years. And she also led speech at Google for 7 years, where she drove multiple research and engineering efforts that enabled Google Assistant and voice search. Carolina grew up in Venezuela. She moved to the US to pursue a master's degree in electronic engineering at University of Washington, and she did her PhD at Johns Hopkins in machine learning. So yeah, just say hi. Just maybe write in the chat where you come from or where you're visiting or connecting. And, let's get it started for Carolina.
Muchas gracias, Benjamin. Hola a todos, y voy a cambiar a inglés por ahora, pero después podemos hacer preguntas en español o inglés. Soy Carolina, estoy en Google ahora, leading 2 sorry, I'm mixing it up, leading 2 teams, the robot mobility and the robot vision team. And here is a little bit about myself. I grew up in Venezuela, and I just transferred to the US when I was doing my undergrad to Washington State University, and eventually ended up doing a PhD at Johns Hopkins in machine learning, focused on speech recognition. And then I was lucky enough to go straight from there to Google Speech. And my first project there was to build OK Google. So that's what I did at the beginning, and then built a team around it. And that was super fun. We built like OK Google for about 100 languages. And yeah, after that, I worked on speech detection, like end-of-speech detection, pronunciation modeling, language modeling, all the different aspects of speech recognition to make sure that the assistant will be able to help you in the car, at home, and even in Google Glass, back when that was the thing. After that, I worked on self-driving cars at Nvidia, and that's the picture I have here in the middle, where we're just testing out the car up in the mountains, which is actually pretty hard. I live now in Colorado, so the roads are pretty steep and windy, and so I was leading there the perception team, so we were basically the eyes of the car, detecting cars, pedestrians, lanes, signs, sign classification, all of that good stuff. And then recently, actually, only 2 years ago, I moved to robotics, and that's what I'm going to talk to you about today. And I have a picture here, one of the robots that we play with every day. And then my other job is basically my kids and my family, and I love doing outdoor stuff with them. And I miss the Caribbean so much. I recently just went for a scuba diving trip there that was amazing in Belize. Highly recommended. I can also give you referrals there if you have any questions on that. So who is Robotics at Google? We are basically a group of research scientists, software engineers, and lab technicians that are all really excited to bring robots to the real world. And this is actually a picture of us pretty much right before the pandemic hit. And we were all in Napa Valley at a cheese-making farm, just hanging out and spending time together. And this was the whole team back then. It hasn't changed a whole lot since then. Our mission is to make robots useful in the real world through machine learning. So we're big fans of this idea of the robot generalist, that is a robot that can do many tasks and help humans in their environment, meaning like at home, at work, in the mall, etc. And we believe machine learning is critical for that to happen. And you might ask yourself, well, where are all the robots? Like, especially since we all grew up with all these movies showing robots helping us in all kinds of ways. And the truth of the matter is that generalizable robotics is still an unsolved problem. And that's what we're working on. So if you think about where robotics is today, I'm trying to capture in this graph how robots help us today. So on the y-axis, I have how robots generalize across environments. So at the bottom would be a robot that is just working on one environment, designed for that robot, usually away from humans for safety reasons, and it's kind of designed for that. And on the top, you have a human-centered environment. That means our homes, our offices, or our streets, etc. And then on the x-axis, I'm trying to capture generalization across tasks. So towards the left would be a robot that is doing just one task, for example, assembling the door of a car, and does it really well. And on the right will be a robot that can do many tasks, like an assistant, right? And so what today, most of the robotics in industry are basically on the bottom left, right? Because they're in warehouses, or they're in car building facilities, and they're just doing one task in a specialized environment. Self-driving cars, I would certainly think, is closest to the top because they're operating in our roads. We're not modifying our roads. They're interacting with pedestrians and with all their human drivers, and we're not modifying our roads for them. But they're still trying to do one task, right, which is get you from A to B in a safe manner. And then finally, robotics at Google is really trying to aim for the top right. So we tend to focus on algorithms that will work across tasks, that would generalize across environments, and we just really believe we can't do that without machine learning. So when I mean, just to make sure that you know what I mean by generalization, we want to generalize across environments, meaning if I train a robot to do to pick up one object, it can actually pick up any other object that is physically possible for it to pick up. If I train a robot to navigate in a particular environment, like maybe the micro kitchen in a Google building, it can actually also navigate my home. And then in terms of instructions, generalizing across instructions, what I mean is literally anything that you can ask a robot to do that is physically possible for it to do using natural language. And many of us actually come from the from other fields like computer vision, speech recognition. There's also some people from just robotics background, control systems. So if there's one thing that we learn about using machine learning, especially the deep learning variants for a new problem, is that these algorithms tend to scale really well with data and compute. So for example, the very first system that we deployed at Google using neural networks was street number detection on Google Street View images. And that's the first column that I have there on the left. And it used 1 billion images just to do binary classification. This was deployed in 2012. And of course, since then, the field has advanced incredibly. And now we can use smaller networks, less data. But we're still talking about 1 million images in order to learn how to generalize across hundreds of objects, for example, in the COCO dataset. And then we also require at least 100 million backprops for good generalization across many tasks. So the fact that it scales well with data and compute is great for us because we know how to do that, but it's also difficult to do this in robotics because you have physical robots with sensors and actuators that actually degrade over time. So that's one of the challenges that we find in robotics. Nevertheless, we think in order to really generalize in robotics, we're going to need to build a system that is scalable. And we also want to make sure that system has the capability of pre-training and fine-tuning. And I'll explain what I mean by this. So for scalable, we mean that we want to enable distributed collection. So you want to be able to have 100 robots distributed in different environments and basically push out to them a model that will then collect data, and then all that data can be sent back to the model for retraining. So that you can scale and see lots of environments. The other one is leveraging all collected data. What I mean by this is that if I deployed a model 6 months ago and collected some data with it, and today I want to try to train a new model, I want to be able to leverage that data that I gathered, even though it was gathered with a different model. And then distributed compute is the obvious thing. At the beginning, we know that every time we're trying a new problem, we tend to start with bigger models and lots of data in order to understand and get some baseline. So we know that we're gonna, if we can leverage distributed compute, then we don't have to worry about that. We can just do training across multiple machines. The other capability I mentioned was pre-training. What I mean by this is that you want to be able to build a somewhat task agnostic model, and then with a little bit of data, adapt it to one task or another task or another task. So you want to be able to need less and less amount of data the more tasks that you're learning. And then, of course, you want to leverage simulation because, as I mentioned, deploying 1 million robots is actually pretty difficult, logistically expensive. It has safety constraints. So we want to leverage simulation as much as possible. So we do that as well. We want to leverage offline training. What this means is that you want to be able to collect a bunch of data and then update your model and not have to collect data every time your model gets a gradient step, right? Because that's less efficient. And then finally, we believe that we need to be able to fine-tune this model as it gets used in the real world so that you can adapt to changes in the real world of the robot itself, the actuators, or just to learn as you're evaluating. Right, so let me get more concrete. So I mentioned generalization across environments and instructions. So here's one example where we're trying to generalize across environments. So this is one of the earlier projects that we did in robotics. It's called learning to grasp from pixels. And this is just a manipulation task. We have a KUKA arm that is trying to grasp objects in this bin and put them in a different bin, okay? And if the traditional approach to do this is to basically have a sensing module and an acting module. The sensing module will basically try to capture the environment, which in this case is the bin, the objects in the bin, anything associated with the image that you're seeing, like lighting conditions. and then also the position of the arm and the gripper. And so the sensing module just builds us an intermediate semantic representation of that environment, which might be this list that I put here. So you might want to have the location of all the objects, the orientation, their shape, their texture, etc. And then you would normally have an acting module, which takes this intermediate representation and produces an action. An action in this case is just where to move the arm, and then whether the gripper should open or close. And what we found was actually that if you want to generalize this across any object, so you throw in there any type of object that is physically possible for the robot to grasp, it's actually hard to come up with a concise representation, and you keep adding things to that representation. And so what we tried instead was trying to learn that API and just have a model that goes from the image, the RGB image that you see here, to an action using supervised learning. And if you think about it, this is a one-step optimization, because what you're doing is you're taking your current state and then you're taking one step and then checking the next state and taking one step, right? What we found that worked better than that actually was to do multi-step optimization. So what you actually want to do is to optimize the entire trajectory of the arm until it successfully picks up that object. And we found that this was better done using reinforcement learning, which is a formulation that is actually designed for sequential tasks and optimizes for delay rewards. So basically, since the goal here would be success would be to pick up the object, then the reward might come, the success might come after many steps of arm motion. So for those of you who are not familiar with reinforcement learning, I was also new to this since I come from the supervised learning community. So I just try to put one slide on it. Basically, reinforcement learning is just this subfield of machine learning where an agent is able to interact with this environment and learn from trial and error. So the agent is going to make actions on the environment and modify the environment and learn from the feedback of that environment. Okay, so the agent in this case is a robot. It performs actions, which would be the movements of the arm and the gripper, and then it takes observations from that environment and get some feedback. And the feedback here is called a reward. And a reward is nothing but a scalar number that tries to capture whether what you did was good or bad. And interestingly, you can have very sparse delayed rewards. For example, in this case, our reward was literally 1 if you can pick up the object and at a certain height, and 0 if you are unable to pick up the object within a certain number of steps. So you might get a reward after many different actions. And then there's many flavors of reinforcement learning, model-free, model-based. We tend to stick with the ones that are model-free, meaning we don't have any model of the world. We literally just learn by trial and error. And even within that, there's many flavors. And the one that we used for this work was a Q-learning-based model using called Qt-opt. The basic idea is that all you're trying to do is learn this Q function. This is the one equation I have in the presentation. It's just a Q function. And this Q function is basically your belief, the agent's belief, that given the current state and taking the action AT, you're going to be able to succeed eventually. So it's an estimate of your expected future reward. And the state here is basically the internal representation of the agent. It could be, for example, your last observation, the last 10 observations, and your last 3 actions, whatever it needs in order to make a decision. And then once you have this function, you know your state, and you can basically search and find the best action to take given the current state and take that step. So if you take a step where you're trying to do the best action to your knowledge at this point, it's called an exploitation step, where you just exploit the information you have so far to maximize your reward. Alternatively, you also do this other type of step called exploration, which is where instead of taking the best possible action, you take a random action simply to understand what would be the feedback and learn more about the environment. And you iterate between these with some probability. So going back to the problem that we're doing here, like I mentioned, we use Qt-opt, and I have a reference paper for you to look at if you're interested in diving deeper. But basically, this is the model. It's just a stack of convolutional layers. The input is an image. It could be more than one image, like the last 3 images. And then it's very similar to ImageNet. The big difference is that it actually has a branch in the middle where you feed actions. And so the idea is you give it the input, you give it the actions, and at the end, you're predicting this Q value function, which is essentially your best estimate of the probability of success, given this is the state and you take this action. So of course, to train this model, we need lots of data. And so we go back to our model where we're trying to scale to many robots. And so we actually set up this farm of KUKA robots. There are just 7 right here. And they were basically collecting data 24/7. We wanted to collect at least 1 million graphs, but this was our first setup. So it took us 3 months. And this was pretty much automated. We simply detected success or failure using a camera that is placed over the shoulder of the arm with an object detection system. So you detect whether the arm has an object or not when it gets to a certain height. And that's it. You basically do maintenance to the robots. Not only do you want lots of data, you also want it to be very diverse. So this is an example of the data that we used. And this was just during training. We just kept basically rotating the different items. And then at test time, you use completely different set of items, of course, to prove that you can achieve generalization. So this video here is showing on the left a supervised approach and on the right, the reinforcement learned approach for this task. Like I mentioned, the goal is to pick up an object and put it on the other bin. And with supervised approach, meaning you just make one decision at a time, given your current image, you get about 80%, 78% graph success. With the reinforcement learned approach, you get about 96% graph success. And that's the paper reference. And the most interesting thing is actually that the reinforcement learned approach does all kinds of things that we weren't expecting. For example, it does these pre-grasp manipulations where it pushes the puzzle out before picking up an object. And this is something that it just learned from trial and error, or it might break the puzzle and then pick up a couple objects at a time. It also does self-correction. So if you can't pick up the object, it will continue to move until it actually does it. It doesn't just restart the episode. And then it's robust to perturbations, right? So it just keeps modifying its actions until it successfully picks up the object. It is also robust to optically challenging objects because we're just using RGB. There's no depth camera here. And yeah, it's able to do this without any modification to the algorithm. I think this is one of the most interesting ones. The algorithm can adapt. If you deploy the algorithm, you can imagine that you can there are changes to the environment that could affect it over time. Like maybe an actuator is not working as well as it used to. And so to test that, we actually tried a bunch of different modifications of the setup. So the easiest to explain here is the one on the rightmost image. So what we did there was we actually just shifted the gripper by 10 centimeters from its original location and just deploy the system that was trained with the original configuration of the arm. And of course, the performance dropped to 43% by doing that. But then we kept gathering data and continuing to train the model. And with only 800 episodes, like about a day of data, it actually was able to go back to its original performance using the modified configuration of the gripper. So that was all really good, but it also took a lot of effort to gather all that data for 3 months on that arm farm. So the question is, can we do better? And this is where the idea of pre-training comes in. So we certainly can do better if we use simulation, and that's what we do. One of the challenges, if you worked in robotics and you train your models in simulation and then try to deploy it on the real world, you know that just doesn't work. Actually, it's known as the same to real gap, and it happens because your simulator doesn't have a perfect representation of the world. In this case, the input to the simulator is the image, right? And the simulated image might not be identical to what you see in the real world. So one of the common ways to approach this is to actually use domain randomization in simulation. The idea is that you just train your model while randomizing the environment with the hope that when you deploy it on the real world looks like one more random environment, and it just works. What we see in practice is that this is actually hard to tweak and decide which part of the environment you want to randomize. It actually makes learning harder because you might randomize parts that are not necessarily going to be changing in the environment. And most importantly, there's still a reality gap. when you do this, you improve the system in real, but it doesn't completely close the gap. So we do have some research threads in the team around sim to real in the computer vision team, in the manipulation team. And this is just one example that I wanted to share. This is called RCAN. And what we do here is that in simulation, you have this large number of randomized environments, and then you learn a mapping from these randomized environments to a canonical representation, which is the one I'm showing on the right. And then when you're going to deploy in real, you also map the real image to this canonical representation. And if you do this, you get about 70% graph success with no real data, just about 3 or 4 days of training. And then when you actually continue to train, once it's deployed, you can get with only 1 day of data about 91% graph success, which is much better than 3 months. Here's another example of a sim to real project. In this case, we actually use cycle GANs. If you have a little bit of data in simulation and a little bit of data on real of the same setup, you can actually use a cycle GAN to learn a mapping between sim and real. And then what you do is that while you're training in simulation, you actually use that mapping to make the simulated images look a lot more realistic. And then you deploy your system on the real world. You get about the same gains, about 91% with just 1 day of real data adaptation. Cool. And all the work that I mentioned before is actually used at one of the robots that we have at Google, which is called the Everyday Robot. It's public. You can look it up. Just search the Everyday Robot project. And it's basically a robot that's like the one shown here. Is a little smaller than the average person, and it's on wheels, and it has just one arm tucked in its back, and it brings it out and does different tasks. And the task that we're actually doing is sorting. So we have real stations like the one shown on the little video on the bottom right. And basically in these stations, people, regular workers, regular Google folks put their trash there in different bins. And then the robot basically goes and tries to sort the trash between compost, recycling, and regular trash to try to reduce the contamination rate on our trash at Google campus. And this is actually used today in multiple buildings. Cool. So everything we talked about so far is just the human gives the robot a task and then it goes and does it. But another way in which humans could help robots is to demonstrate how to do an action, and then you can learn from that action. So we have some work in the team also along these lines. We have a teleoperation tools team that basically enables robots to learn from human demonstrations. And so we built all these tools. This is Johnny, who leads the team, and he has a VR setup. And with the joystick, he's basically moving the arm, and the robot moves in wherever it is located in a different building. And it can send actions to the robot. And then we collect all this data as demonstrations that you can use with imitation learning to try to get the robot to do this on its own. This was actually one of the projects that benefited the most from the lockdown during COVID time, because we thought we had it all figured out. But then when we started working remotely and the robots were really at a different location, there were all kinds of problems that came up that we didn't realize we had. So it accelerated a lot of the features. It brought up a lot of the bugs. And so today is a lot more effective. So you can fully operate the robots remotely, and they have a way to reset. And actually, eventually, after a few months, we decided to bring some of the robots home and try to play with the robots and see what kind of things we could do at home. So the team actually prepared a video that I want to share with you guys. And I hope the video comes through here. Cool. Let me make sure this moves. Okay. So one other thing I wanted to share with you was an example of generalizing across tasks in a very different robotic platform. So we also work with quadrupeds, and this right here is Locomotion. Is basically a robot that is about 30 kilograms from Unitree. It's about the size of a dog. And in this work, we're trying to generalize across tasks by imitating skills done by animals. So the motivation here is that animals can do all kinds of really agile skills. And the question is, can we learn from them? There are definitely examples of robots that can do agile skills in the real world. I'm sure you all have seen this. This is animal trying to trek through like some outdoor environment that is unstructured. We have Atlas in the middle doing parkour, and then that's MIT Cheetah doing a flip. And sure, we can have all these examples, but each one of these cases was actually took a lot of time to design, and it was actually require a lot of expertise on the robot itself and the skill itself, and a lot of fine tuning for this particular setup that you're seeing here. And so what we want to do is actually try to learn how to do this without having to do it once per skill and per robot. So instead, we are trying to learn how to imitate animals. And so we start use a mocap system where you put like tags on the animal on different joints, and then you have a camera system that captures the trajectory of each of those tags. And that gives you the motion data that you see on the top left. Now, the next step is we actually have to do motion retargeting, which just means map these key points in the animal to some key points in the robot frame, because you might have different joints or just slightly different configuration of the robot. So that gives you this reference motion. And then the next step is to actually use reinforcement learning to try to imitate the reference motion in simulation. Again, here we'll leverage simulation first. And then the last step is to actually deploy that on the real world through domain adaptation to get the image on the bottom right. Again, here we see that there is a sim to real gap. And if you just train in simulation and deploy it, it won't be enough, and you need to do some domain adaptation. So let me talk a little bit more about this step, which is the learning step. So here we're actually using reinforcement learning as well. In this case, the observations from the environment is just the robot itself. And the observations are joint angles, roll, pitch, yaw, and also the reference motion that you're trying to track. The actions are the desired motor angles of the different motors in the robot. The reward here is actually a continuous reward that is basically minimizing the reference, the tracking distance between the reference motion and the simulated robot. And then we simply terminate the episode when the robot falls. The policy is actually a pretty simple two-layer fully connected neural network. And the algorithm that we use here is PPO, which is proximal policy optimization. It's one of the most common algorithms used in reinforcement learning. And for the last step, which is domain adaptation, so the main sim to real gap here is actually the dynamics might not match between simulation and real. And so all of the parameters that are usually different are motor friction, motor strength, inertia, mass, latency, and lateral friction. And so again, here, one of the most common approaches is to take these parameters, randomize them in simulation, train your model with these randomized parameters, and hope that when you deploy it in the real world, it actually represents one of these randomized configurations that you use in training. We found that this wasn't enough to close the gap, and instead we proposed this strategy optimization approach, where you take those same parameters that you're trying to randomize, the mass, inertia, motor strength, etc., and you put them in a vector mu, and then you actually feed this as you're training your policy. And then what you do is, as you're learning your policy, you're also learning an embedding Z that is trying to capture the different dimensions in which your dynamics can change. And so the idea here is that you're essentially learning a policy that is specialized for each one of these locations in this embedding space of the parameters. And the policy is just trying to predict actions given the state and the goal and these dynamic parameters. And when you deploy it in real, you of course don't have the real parameters. Otherwise, you would just put them in simulation and train that way. And so what we do is that we actually search in this embedding space until we find a setting that actually gives us the same performance in sim and real. And here I have some examples of the system. So on the left is just a reference motion. The middle is what happens when you train in simulation and it works perfectly in simulation, but you just deploy it in real without any domain adaptation. So you can see that it works, but then eventually it actually fails and falls. And then on the right is the one with after adaptation, which is a lot more robust, and it will keep going for a long time. And here are some other results using different types of actions. So dog pace, dog trotting, spinning, and backwards trot is the same as the trot, but just played in reverse. And this is all using the same algorithm. It's just in each case is optimizing for the trajectory, for reducing the tracking error between the simulated robot and the real motion that was captured. And what's really cool is that you could also do this with like animated motions. So we have an artist do these motions that you might not get a robot to do, and you can just reproduce those in the robot as well. And all of this code is actually available in GitHub. So if you're interested, you can check it out there. Actually, a lot of the reinforcement learning algorithms that I mentioned are actually all available in this DF Agents library. And this is just a reliable, scalable, and easy to use reinforcement learning library in TensorFlow. If you're new to reinforcement learning, it's actually great because it has all kinds of collabs and examples and documentation and toy examples to help you get started. And then if you already use reinforcement learning and want to add a new algorithm, it's easy to add as well. And you can contribute to this library. You can just install it with pip install TF Agents. Also, we use this simulator PyBullet. So if you're not familiar with it, this is just a fast and easy Python module for robotic simulation with a focus on sim-to-real transfer. The author of this simulator is actually my team, and he continues to work to improve the sim-to-real gap. And it also contains a lot of the robots that we use. I didn't mention today, but we also have this robot in the middle, which is the miniature, and some of the other arms. And again, you can just download it using pip install PyBullet. And I won't have time to talk about all of the other projects that we have, but just wanted to give you a flavor of other things that we look at. We're interested in visual locomotion, which is just taking our quadrupeds and navigating any unstructured terrain, like around outdoors, like in steps and stairs in cluttered environments, using camera input. So on the bottom left, I have Leica Go doing steps for the first time. And then we also care about safe learning. So many of these examples that I mentioned, you're doing some episodes in the real robot, and the robot is going to fail in some cases. So you want to be able to do that in a safe manner. So you want to fail gracefully, and you want to be able to reset to continue training without human intervention. We also work on differentiable sims, so expanding PyBullet to actually include, enable you to backpropagate gradients all the way through the simulator. And this is actually really important to reduce into real, and also to just improve data efficiency for RL. And besides reinforcement learning, we also use MPC quite a bit, actually, evolutionary strategies and imitation learning. The larger group of navigation, which I also lead, expands from locomotion to work also with the wheel robots. And one of our main focus is to actually enable the robot to drive efficiently in a map when there are not only static obstacles, but dynamic obstacles, so social navigation. So we've invested a little bit on simulation of humans, and then this is an active area of research, being able to navigate not only safely, but also in a socially acceptable manner. And then we also want to learn how to navigate to accomplish a task. So on the bottom picture, if I just ask the robot to wipe the table, it needs to be able to know how to navigate without anyone specifying the coordinates to navigate to in order to accomplish that task. And here again, we use all of these techniques, RL, imitation learning, MPC, but we also add high-level planning research. And there's a lot of benefits and advantages to the work that I presented, but there's also caveats and areas of improvement that I want to highlight for you guys. It requires lots of data and compute, as we've seen. It requires some on-robot online adaptation to work in the real world. We haven't yet successfully done zero-shot transfer from simulation. Many people think reward design is hard, although we've seen examples where if you just design a simple sparse reward like 1 if you succeeded at picking up your object, or 0, we've seen that works, but it can be more difficult when for navigation, for example. Like, how do you encode social navigation in a reward? System complexity is high. This is kind of a black box. You have an input, which is usually your sensors, and your outputs are actions. So when things go wrong, it can be hard to debug. And yeah, the reason why we need on-robot online adaptation is because sim-to-real challenges still remain, and they are across vision and dynamics. So if you combine them, then it's even harder. And currently, we're tackling like a few tasks at a time. And what we're really focusing on is on building a multitask system with zero-shot transfer to a new instruction, so it learns to generalize without having to have seen that data during training. But overall, we're really excited about a new model for robotics that is designed for generalization. And we think that needs to include scalable data-driven learning, task-agnostic learning, pre-training in simulation, and learning from past experience, as well as enabling fine-tuning in the real world to learn from new interactions. And since I'm here, and I wanted to just also mention that at Google, we'd really like to hear from all of you. We have opportunities for faculty and students. For faculty, many people don't know, but we have like the Research Scholar program, which is basically a grant for early career faculty. We also have awards for folks working on populations, folks from underrepresented communities working in research areas that we're interested in. And then we have this visiting researcher program where basically faculty take like a 6-month or 12-month sabbatical, and then they go work at Google in a research project of their interest. And you can find all of that at research.google/outreach. And then for students, pretty much everyone knows that you can come and do internships, but there's other things also. There's like PhD fellowships for students who are doing excellent work in their PhD and is relevant to Google's research. We also have some mentorships like Explore CSR or the CS Research Mentorship. Some of them are targeting helping underrepresented communities in CS, and of course the internships. And that is all I have. Thank you very much, and I'm happy to take questions now. And if you think of questions later, you can also email me after this conference.
People can put applause emojis or whatever you want in the chat. I'll do the applauses. Yeah, that was really awesome. There was a lot of yeah. I mean, there's just like so much stuff going on. I'm gonna switch it up into Spanish for some of the questions, but feel free to, because some of the questions are phrased in Spanish, but also you can answer them however you want. We're gonna go over some of the questions, and these are in the Q&A. Actually, most of the questions are in English, so I'll just do that. Okay. Okay, so our most popular question right now is from Abel Mendiola. What is the difference between Google robotics approach and Boston Dynamics approach?
Yeah, I mean, I think that from my understanding, and I've seen a couple of talks from Boston Dynamics, is that we are basically trying to build algorithms that are not just trying to perfect one motion or one task, but it's trying to generalize across many tasks. And so we don't spend a lot of time fine-tuning so that the robot can walk perfectly if that's the only task that is there. I mean, we just do it enough so that the robot can walk safely. But then if that approach only works for walking but doesn't work for trotting, doesn't work for turning, we probably won't spend a lot of time on that. So they use a lot of like classical control and also include a lot of perception. So that's where the machine learning comes in perception and trajectory prediction. And then the rest is more classical control and a lot of fine-tuning. That's my understanding.
We have a lot of questions. There's like 11 questions. So, and there's probably going to arrive more. I'm going to pick not the second most popular one, but a very related question to what you just answered. So Antonio del Rio Chanona asks, reinforcement learning seems to get all the hype, but control theory, NPC, is most of the times better in robotics. Could you share your opinion in this respect?
Yeah, I mean, we have certainly the same like argument within our team. Actually, we have folks from both the control theory background and both and experts in NPC, and folks working on reinforcement learning, and folks working on imitation learning, and we're just driven by results, right? A lot of the work I presented today is focused on reinforcement learning, but we certainly have a lot of other work using NPC. And what I've seen so far from my own experience working on navigation and locomotion, which is one of the most safe sensitive tasks to do, is that NPC is an amazing low-level controller, and then we actually tend to use reinforcement learning for higher level decisions. So for example, you might use reinforcement learning to decide what the next trajectory should be, but then you execute it with NPC. And this is work that I didn't present today because it's more recent. So I think we probably can combine the control theory side with the reinforcement learning side to get more generalization. And of course, perception is an important part as well. So we don't have a different answer today.
We have another question that is related to, I guess, like the state of the industry and other, like, other robots. It says, Monica Rodriguez asks, what do you think about the Tesla bot announcement? Is it possible to release this type of robots in the current state of the art for humanoid robots? Smiley emoji at the end.
Yeah, I don't know anything about Tesla. I think it's really cool. I think the more people working in robotics, this is a very difficult field. So I think the more companies and the more people in academia working in robotics, the more we can learn from each other. We actually collaborate a lot with academia from different schools in the US mostly right now to try to find areas of common interest. So I don't know what Tesla would do about like open sourcing this robot. There are some robots that you can buy and then basically modify their algorithm, like all the Unitary robots anyone can buy, and a few from Boston Dynamics, right, as well. Yeah.
Yeah, we have a similar related question about like this idea of open sourcing robots, buying robots. So we have an anonymous question. What is your advice for young researchers, students with low resources for getting into robotics? What are areas of robotics that you think are fertile for low-cost research?
Yeah, I mean, I think nowadays a lot of students can get access to a lot of compute through the cloud. So I think this is a different time to when I did my PhD, and if your university didn't have enough machines, well, that's it. So I would say a lot of the research in simulation is actually really valuable, even though there is still a gap between sim and real. Most of our algorithms are trained in simulation first, and if they don't even work in simulation, forget about the real world. So I would say working on robotics in simulation and using all of this cloud resources that you can now purchase fairly cheaply from Amazon or Google. Yeah.
Yeah, that's some great advice. We have another question. Let's see. The questions get voted, so they like move around sometimes. So trying to find the next one. So Cesar Magaña asks, how far is research from using reinforcement learning techniques for a lifelong learning system?
Yeah, I mean, it depends what you mean lifelong learning, meaning like you deploy it and it just continues learning on its own. I mean, we do have a system like the one I presented that is like that, but it's still kind of targeting that one task of grasping and sorting, right? I imagine what you mean is like a system that can do all of the tasks and then continue to learn. And I would say we're still far. We're still far, like 5+ years from it.
Yeah, I mean, well, 5+ years. Yeah, there's a lot of work to do, right?
Yes. In generalization in the real world is hard. And And so we're still like all of these robots are still operating, for example, in our offices. But I imagine if you really want lifelong learning in any environment, you would have to go to the messy world. You would have to handle, for example, the Woo robots right now wouldn't be able to go down the stairs anywhere. So it's still going to be limited. And even the quadrupeds that can go down the stairs, there's certainly environments where they would trip and fall. So yeah.
We have another question, and this is an anonymous question. How do the teams decide which problem approach with a robotic solution? So yeah, like how do you pick problems or the actual like problems you want to tackle with a robot?
Yeah, so I mean, what we've done so far is that we get together and think about problems that will need generalization in order to work. For example, we create benchmarks out of them. So the sorting case was the first one that we did, but since then we moved to like basically benchmarks that include, for example, doing anything I ask the robot in a cafe, right? And then that means that you have to generalize across many actions. It needs to work in any cafe in our buildings. It's still limited, but it's a way to capture some generalization. Once we decide a benchmark like that, it's free for all. Pretty much anybody tries whatever they like to try. And so there's people, like I mentioned, focused on NPC. There's people focused on reinforcement learning. There's people putting together the two. And so we just have benchmarks with very clear evaluation. And then we can just see what's working best and what's not. And it might change over time.
We got one question from Abel Mendiola. Are there robotics products from Google in the market? So far, I have not heard much about it.
Not really, not the kind that I presented here. I mean, Waymo is a robot, right? If you think about it. So that's the closest thing, and it's not yet in the market. The Google Assistant or all of those other devices that are being put out in the market could be considered like a robotic system, but nothing like what I presented today. Right now, we're basically a research team. That's why we're in research, and we're trying to just advance the state of the art in robotics and see where that takes us. We're basically like at the beginning of where the speech team was maybe 15 years ago, where we were just exploring. There was no speech product. I think Google 411 was our first speech product, and that was the thing that will ask you, what business do you want to reach? In what city? That's where it was 15 years ago. So we're in that stage in robotics right now.
Yeah, so there's a lot of exploration still to do, right? And things to figure out. I think there's also, I think, a related question that I'm gonna like ask, and this is from David Augusto Galvan Alvaro. Have you reflected on the ethical implications of your work? And if so, what are the measures you're putting in place to control the impact of this research? And thanks, great talk.
Yeah, I mean, we do have like a group at Google that is focused on reflecting on the ethics. It's certainly not part of what I'm doing every day. But they basically are looking at how governments think of robotics, how people think of robotics. There's also like an HRI component, how do robotics interact with humans. So this is all very early stages. So yeah, it's not my main job, but there's certainly some folks at Google looking at those aspects.
I have two other questions that are more like technical and around some of the things that you were presenting. And so one question is from Enrique Zucar. How long does it take for the reinforcement learning on the object grasping task? How much does it take to learn? And the hardware used, Yeah,
I mean, I think that the fastest time that we used is about a week. I'm actually just a manipulation team, so it's not my team, but we use similar techniques. In our case, it takes about 2 days. The manipulation task is harder. So what I've heard is about a week time in simulation, and then a day of online adaptation on the real world, on the real robot. And then we use TPUs, but I can't share more than that, other than we can do all our training in TPUs.
The other technical related question is from Jorge Agustin Alvaran Morales. He says, thanks, great presentation. As far as I understood, motion data has to be fed into the robot. Is there any research on robots learning their own mechanics, motion rules or motion data? And I think you did present something related to that, right? But yeah, what are your thoughts?
So no, I mean, in the manipulation case, literally the input is the image and the, let me see if I can go back. In the reinforcement learning method here that we used, I would say probably the best one. Yeah, so this is the model. It basically just uses the input images, and then you have a set of actions that you sample, and then you score those actions using a Q-value function. I believe the actual state of the robot is also fed here, but it's not added in this picture. And that just means the location of the arm and the actual state of the gripper, whether it's open or closed. And that's all that gets used here. And then what you're predicting when actions is actually the next location that you want the arm to be at, and then you might use a low-level controller to get the arm to that location.
Yeah, so it's almost all entirely just from pure pixels from images, right?
Yes, it's very end-to-end.
We have another question that is around the actual computer vision part, and this is from Abel Mendiola, and he says, what's the difference between the hard Cascade, Yolo, and the algorithms you're using for object recognizing?
Yeah, so actually in this particular job, in this particular system, there's no object recognition. You just give the RGB input and you just predict the next action, meaning the location of the arm that you wanna be at. So there's no object recognition. Now we also have, like I mentioned, we set up benchmarks and many people try different things. And so I believe that some of them are using Yolo for doing the obstacle detection and orientation and whatnot. And then you use a regular controller to try to get as close as possible. And they use depth estimation and all that. That is the system that I'm not familiar with, but it's using all the traditional perception plus predicting an action using supervised models.
Yeah, so it's really incredible that it's just essentially just going directly from the images, and I mean, and there's other ways you can try it out, but it's just happening almost end to end, right?
Yeah, which is one of the things that could be seen as a challenge, which is when things go wrong, then how do you know whether it was, what part of the system was not working, and or if you're training your model and nothing works, then what do you do? So, and reinforcement learning tends to be kind of unstable. So it took a lot of iterations to get to this model. But it does work now pretty reliably. And it uses this QT-opt algorithm, it was introduced in this work. We've also used SAC, if you're familiar with other reinforcement learning methods to do this task, and it works pretty close to the QT-opt algorithm.
So we're just got to the hour. We got to cover a lot of questions, and we got to just hear a lot of amazing work from Carolina. Do you want to just give one last whatever any message you want to give to the participants before we move on to posters or booths, or you could just say thanks, bye. That's also good.
You mean me?
Yeah.
No, I'm just really excited to learn about other folks' work in this workshop. And my main message is that if you're excited about robotics and you have a background in machine learning, that's all you need. You don't need to be an expert in robotics. You can start working in this field. It's still in baby stages, so it's a great time to get involved with it. I invite you all to reach out to me if you're interested, and give it a try to some of the open source tools that I share.
Yeah, well, thanks a lot, Carolina. I'll do the virtual applauses also, but we also had a lot of emoji applauses. And let's move on to the next session. Thanks, everybody.
Bye, guys.